We're going to do a small lesson on Lewis structure, molecular structure, dipoles, and polarity lecture. So the way that we're going to introduce this is by actually looking at some examples. We had talked about how certain atoms that are that don't have a great electronegative difference, that rather than being able to be strong enough to pull the electron off of one atom and take it for itself, instead that they share electrons. And the perfect example would be two of the same atom where both are equally strong. So we have hydrogen over here, and it tells us we have two hydrogens. They both have one valence electron. And ultimately, the story has always been in chemistry that we want to have hydrogen have a full valence shell. Hydrogen just has one shell, so that means that it actually only wants to have two valence electrons. So is there a way that we can arrange these hydrogens so that these hydrogens can share their electrons so each of them has two? And the answer is yes, we can. If we take one hydrogen, place the electrons in between them, now these hydrogens both have two electrons. And I use this circle to show that. So this hydrogen has the two electrons to fill its valence shell and reach that state of nirvana, and this hydrogen does also. And they do that by sharing their electrons. Rather than drawing dots and circles like the Lewis structure, this is an example of a Lewis structure, we can write a molecular structure, in which case what we do is we take two dots and represent them as a dash. So wherever I see two dots, that becomes a dash. And in this case, we have two hydrogens that are bonded together with a covalent bond, and we represent that with a dash. Because these have no electronegative difference, for that reason there is no dipole. And the type of bond this is a non-polar covalent bond. Let's do another example. In this case, I have two chlorines. So both chlorines have the same electronegativity, so I know that in this tug of war, one is not going to be stronger than the other. Based on the periodic table, I also know that each chlorine has 7 valence electrons. Remember, chlorine has 3 shells, and so in its outer shell, it wants to get 8 valence electrons. So same question, can I rearrange these atoms so that it can have 8 valence electrons? And usually the spot where things tend to bond is that single electron that you'll find in a region. So if I organize the chlorine, here's our 7 valence electrons, so that the other chlorine, here's the next chlorine with 7 valence electrons, that they would share these electrons. You'll notice that again, each of these chlorines, thanks to this sharing, has 8 electrons, and those are 8 valence electrons. In this case, I would again draw a molecular structure where these two have been bonded, and I do that with a dash. However, I'm not going to forget that I still have valence electrons, but they're not bonded to anything. And because they're in pairs, they don't need to be bonded with anything. They're perfectly fine by themselves, and we call that a lone pair, because they are perfectly fine being alone. Again, where you have that single electron is usually where the bonding happens. So if I were to take a step back and look at this molecule, the whole molecule, and would approach it from different sides, would I approach a region that is more positive and one region that is more negative, or are they all equally negative? And the answer is more or less you're going to have an equal distribution of electrons on the outside, and because of that equal distribution, this is considered non-polar covalent. Going back to our original slide, this one here had no electrons on the outside, which means that is there one region that was more negative and one that was more positive? And the answer is no. They had an equal distribution, being no electrons on the outside. So now let's try carbon with 4 hydrogens. Again, we're going to draw our dot structure for carbon. It has 4 valence electrons. Hydrogen, we have 4 of them, each have 1 valence electron. Remember, hydrogen wants 2 valence electrons, but carbon wants to have 8. So again, as I said, those single electrons are the place where you're going to have your bonding happening. And usually we're going to put the one that is the most electronegative in the center. So I have chlorine in the center. Can I arrange these hydrogens where they can share the electrons? So carbon has 8, so there's an electron, here's an electron from hydrogen, here's an electron from hydrogen, and here is yet again an electron from hydrogen. Do these hydrogens each have those 2 valence electrons that they want? And the answer is yes. Does carbon have the 8 valence electrons it wants? And the answer is yes. These circles are often seem a little bit childish, but actually doing those guarantees you always have it right. So wherever we have those 2 shared electrons, we're going to put a dash. So carbon with hydrogen starts looking like this. Okay, now in this case, do we have shared electrons between carbon and hydrogen that are equally distributed? And the answer is no, because hydrogen, you will notice, is a lot less electronegative than carbon, which means that we're going to have to show a dipole. You notice how there's no electrons over here, so that means it's a more positive region, and carbon is pulling the electrons towards it. So we're going to create 4 dipoles, 1 for each bond. And you'll notice that on the outside of the molecule, if you were to approach it from any of the outsides, is there one region that's more negative than the other? And the answer is no, they're all positive. So we consider this still to be a nonpolar molecule. Okay, in this case, we're going to call it a molecule. They do have polar bonds, but they make up a nonpolar molecule. So we call that polar covalent bonds. But the way that they're actually distributed results in a nonpolar molecule. Let's try one more. In this case, we have hydrogen, we have carbon, and we have chlorine. In fact, we have 3 chlorines. Okay, so how are we going to arrange these? The way that I like to do it is which is the element that has the most bonding sites, and carbon clearly has 4 bonding sites. I can tell that because you just have an individual electron in each region. So in this case, I can have hydrogen be bonded here. I can have chlorine be bonded here, another chlorine to be bonded here, another chlorine to be bonded here. Let me check whether or not the amount of electrons that each wants fits. I know hydrogen wants 2, so that takes care of that. Chlorine wants 8. This chlorine wants 8. This chlorine wants 8. And does carbon have the 8 that it wants? The answer is yes, it does. So in this case, I write HCCl with dots, Cl again with these 3 lone pairs. Okay, now let's take a look at the dipole over here. In this case, we know that hydrogen has very little electrons, but do you notice how many electrons are on the outside of chlorine? So looking at my periodic table, I notice that chlorine is further to the right. For that reason, it is more electronegative. And so I know that chlorine is going to grab those electrons towards itself from carbon. So chlorine is going to grab those electrons from that. So in this case, this clearly shows that this is a non-polar a polar molecule, because of how it is arranged, these polar covalent bonds don't even out or don't cancel each other out.